Up until now, we've been working under the assumption that light travels in straight lines. However, in reality, light has a wave-like nature, and that leads to some interesting behavior when it encounters obstacles or openings. But you may ask, what is diffraction? Let's do a simple experiment. Let's imagine we have some sort of metal slit through which we propagate light. So here you can see a light, which by itself has a varying amplitude. So superposition of these waves would give us a light. And let's right now see what happens when this light moves through this tiny space between two slits of metal. As we can see, when the light is squeezed through this tiny hole, we can observe this ring-shaped pattern. So as the diagram shows, diffraction is the bending of light waves as they pass through an aperture or an opening or around the edges of an obstacle. When a wavefront encounters an obstacle, like here, each point on the wavefront acts as a source of new secondary wavelets that spread out. This is known as Huygens principle. The secondary wavelets interfere with each other, creating a characteristic pattern of bright and dark regions called a diffraction pattern. So what you can see here is the diffraction pattern. Diffraction isn't limited to sharp edges. It occurs whenever a light wave encounters a change in the medium, such as passing from air to glass, or encountering a change in density. So you may ask why diffraction is important. So let's do a simple experiment. Let's say we have a red laser of 650 nanometer wavelength. We have our optical system made of optical aperture and converging lens. Let's shine a laser through our optical system. Our lens will converge our point laser source to a point, ideally. However, ideally, we won't observe a point. Instead, we'll observe some sort of ring-shaped pattern, and this what we call diffraction pattern. This diffraction pattern is characterized by the very intense point in the center of the image, of the formed image, and decreasing intensity as we move further from the center of the image. So diffraction is actually responsible for image formation in any optical system, including telescopes, microscopes, and cameras. The light waves passing through the aperture of these instruments diffract and interfere, creating the image we see. Diffraction, it's important to note that diffraction is very much related to resolution, and especially to the resolution limit of an optical system. Diffraction also sets a fundamental limit on the resolution of any optical system. This means that a minimum size of detail that can be resolved, no matter how perfect the lens or mirrors are. Many times we speak about optical systems. When we speak about optical systems, many times we speak about diffraction limit. Diffraction limit means a fundamental limit on the resolution of any optical system. This means that there is a minimum size of detail that can be resolved, no matter how perfect the lens or mirrors are. So here you can see diffraction limit formula. It means it quantifies the smallest detail we can resolve with our optical system. So the diagram shows the formula for diffraction limit, delta x, which depends on the wavelength of light, lambda, and the numerical aperture, Na, of the system. So as you can see, a larger numerical aperture and shorter wavelength would lead to a better resolution of a system. As you can see, for example, if you would fix, for example, lambda to some certain wavelength, for example, 650 nanometers, then the only parameter on which you can play to improve your resolution of your system is to increasing your numerical aperture.